All right, so what I want to do, so far we've been taking a look at differential equations, and in looking at the differential equations, you've actually solved some easy ones, you've checked the answers for other ones, and now you've looked at slope fields, all as a way of sort of figuring out how to solve differential equations. Today we're actually going to learn how to solve them algebraically when they're more complicated. But what I'm going to do first is sort of go back and I'm going to show you what the answer is. And then I'm going to show you that it makes sense given the slope field. And then we're going to get the answer. So it's going to be a little weird. Like, I'm going to tell you what the answer is, and then like 10 minutes later, we're going to find the answer, and you're going to be like, yeah, but we already knew that. But I'm doing that on purpose, okay? So like, I know that I'm giving you the answer, and then we're going to show how to get it, but I'm doing that so you believe me that the strategy I'm going to show you works. And then we'll do differential equations where I don't give you the answer. Is that all right? Okay. So the solution to this differential equation is x squared plus y squared equals some constant. And there are two ways to show you that that's the answer to the differential equation. If I want to show you that it's a solution, what do I need to have? The derivative and the function. I don't need the second derivative here because it's just a first order differential equation. So one of the things we could do is we could solve for y. Square root of c minus x squared plus or minus. Yeah? Yeah. All right. Now, you really do need to do both branches, the plus branch and the minus branch. I'm just going to deal with the positive branch for now. And actually, that's all I'm going to do. If you're interested, you can do the negative branch, but I think I'll convince you that the positive branch works, and then you could check the negative branch when you're bored at home. All right, or in class. So I'm going to rewrite this as that, and now I need the derivative. Say again?
1/2 c minus x squared.
Oh, yeah. I want to show you that that's true, so I need to find the derivative and then show that the derivative equals that. Yeah, you're absolutely right. But we're given that, so stating the given is perhaps a little obvious. But you're absolutely right, it's true. Raised to the...
-1/2.
But don't forget...
2x minus 2x.
Where's the negative 2x come from? The chain. I'm going to multiply negative 2x times 1/2, and I'm going to get negative x, and I'm actually going to make this c minus... Whoops. I could say to the 1/2, but I'm just going to say to the square root of that. How'd I do? Is that derivative look right? Algebraically written?
I'm confused why we try to solve for y in the first step.
How did you want to take the derivative?
I just do 2x plus 2y equals c. C isn't the function.
Look, if you want to do that, can you hold on for 5 minutes? You're doing it wrong, but your idea is right. Mm-hmm. Okay? So Claire has a good notion of maybe another way of doing it, and I think you're going to actually see Claire's thought is a little more clever. It's going to take a little bit more correct calculus, but that's okay. All right, so I have y prime. Let's see. I want to check to see that y prime is equal to negative x over y. So I have y prime, and I also, you found for me what y equals. So I'm going to plug in and check, right? So negative x over square root of c minus x squared equals negative x over square root of c minus x squared. That was an easy check. That worked out really well.
Wait, sorry, how do we go from the y prime equals negative x over y because we wrote it up there?
Mm-hmm.
And then, so he plugged that into dy over dx. He plugged the y prime into dy over dx.
So here's yellow, right? Yellow goes for yellow. And then negative x over blue.
Yeah, that's right.
Okay, and that works. All right, Claire. let's do it another way. I can show you the same thing by taking this equation and taking the derivative. Now, you started by saying,
2x plus 2y.
okay, I love 2x.
2y times y prime.
2y times y prime because we are doing
The derivative.
Little
Number 10
implicit.
on the DOA.
Little implicit.
Oh,
number 10, which Mike tells us is implicit differentiation. The derivative of c is 0. Let's do a little algebra. 2y times y prime is equal to negative 2x. Divide both sides by 2y, which is equal to, whoops, too many negative signs. Erase. Negative x over y, which is exactly what we wanted to show. I actually think your way of doing implicit differentiation is a little quicker and a little more clever and a lot less algebra. So I sort of like that. Yeah. So there are two ways of doing that.
It doesn't really help us to find y prime. Oh, my gosh.
We just showed, we said, look, what's y prime equal to? Y prime is equal to negative x over y. And that's what we wanted to show.
Mm-hmm.
So we got it. Let's see.
Much quicker.
Yeah. So
You want to go back and marvel at that? Is that?
Like,
It doesn't work for all of them.
Yeah.
Okay.
Do implicit on all.
Sometimes it works and it's nice and it's clever to show that that's the answer. But we're going to actually develop strategies today that will work for all of them. This just so happened to be a strategy that worked for this one. And it was good. I'm glad you said it. Let's go look at the slope field. Remember, this is the slope field from yesterday, and you liked this. This was a pretty graph, right? So if I take that slope field, can you see graphically what the solution looks like to that slope field? Yes, no?
yes.
What does it look like?
A circle.
Yeah, some sort of circle maybe.
Which is what? It's like an R squared.
So when we say y prime equals negative x over y, and we say that the solution is x squared plus y squared equals some c, that's exactly the equation of a circle. So let's think about, we have to pick a circle. I'm going to pick an easy one. One of the solutions could be x squared plus y squared equals 25. Give me a point on that circle. 5 squared plus 5 squared is going to be 50.
4, 3.
0, 5 would work.
-5.
I'm going to try to avoid those zeros. I'm going to pick 4, 3. So this tells me that the slope at 4, 3 is around negative 4/3, and that's steeper than 1, right? If I pick the point 3, 4, the slope at 3, 4 is about negative 3/4, right? Does that work so far?
The slope at 25
At 3, 4.
is what? Is about
Negative 3/4.
Okay.
Likewise, I could take like negative 3, 4. At negative 3, 4, the slope should be about 3/4, and so that works. So everything that we've learned about slope fields works with this differential equation and the solution that we picked. So I'm hoping that you're convinced that the solution to this differential equation is x squared plus y squared equals c. Is that okay?
Yes.
Mike says yes. Eva? Brittany B? Helen?
Mm-hmm.
All right. So now we're going to actually learn how to solve it analytically. And this is what we've sort of been working up to for the last 3 days or so. And it's a strategy called separation of variables. And I'm going to start with dy dx equals negative x over y. And I don't know what I was going to say next. All right. And I'm going to use this strategy, separation of variables. The strategy actually needs a proof. I'm not going to give you the proof. You're actually going to think that you can just do it and there's no problem doing it. Unfortunately, that's not the case. So you might have a math professor next year who's inclined to prove it to you, which is totally fine and acceptable. I'm not proving it to you, okay? To use the strategy separation of variables, the important thing is to get all of your y's and dy's on one side and all of your x's and dx's on the other side. So it's really to like group like variables. So how could I start by doing that?
Negative x times dx equals.
Okay, so Mike's almost like cross multiplying, right? You can multiply both sides by y and multiply both sides by dx, and you get something like that. Now, the problem with that is that dy dx, it's a single entity called the derivative, and you can't really break it up without the proof that you can. If I didn't tell you that it needed a proof, would you have thought that you could do it? Pretty much, right? And that's pretty much the reason why I'm not going to prove it to you, in addition to the fact that it's a pretty
Is it a long proof?
it's a higher level math proof. I would even backtrack and say I don't know that next year they'll prove it to you. It might be in an analysis course when you go back and prove everything you learned in calculus. Right now, the goal is just to convince you of what's true and that it works and that you don't have any huge misgivings about this strategy. So let's use the strategy, and then hopefully you won't have any misgivings, and we'll practice a little bit more with it. I have two equivalent, the left and right equivalent sides. If they are equivalent, then I can actually take the antiderivative of both sides. The antiderivative of y dy, go ahead.
Y squared over.
Okay, 1/2 y squared Eva plus, and I'm going to call it C1, and you'll see why in a second. Over on this side, I get negative, what's the antiderivative of x dx? And I'm going to call this C2, because they're different constants. They're not the same constant. So 1/2 y squared plus C1 is equal to negative 1/2 x squared. And I'm actually going to say plus C3, because if I multiply a constant by a negative, what does that do?
Wait, wouldn't it be minus?
I'm asking the question. So if I multiply a constant by a negative, what does that do? It just makes another constant that happens to be negative. But what if the constant was positive? Was negative? It is positive. So a constant just represents something that you're adding. It doesn't represent the sign, so that's why I'm going to say plus C3. I'm going to get x's and y's on one side. And this, you could solve for y. I'm going to get x's and y's on one side in this case because it's going to lead to the solution we're looking for. I'm going to have 1/2 x squared plus 1/2 y squared is equal to C3 minus C1. Well, you know what a constant minus a constant is? It's just another constant. And then I'm going to multiply everything through by 2. X squared plus y squared. You know what a constant times 2 is? Just another constant. I'm actually just going to call it C this time. And guess what we just showed? The solution to that differential equation is x squared plus y squared equals C, which is exactly what we knew it was going to be. Is that all right?
Yeah.
I didn't give you the answer that time. We got the answer. I'd love to do like 2 or 3 more problems, like just to walk through them. Do you want to ask a question on this strategy yet, or you want to try something else first? All right. Let's see.
I do have one question.
Yep.
Because you said that you want to isolate the different variables on either side of the equal sign. So do you only bring them back together when you're isolating the C?
So the first strategy of separation of variables is to group the the y's and the dy's and the x's and dx's on opposite sides. Once you do that, then you want to do one of 2 things. Usually you're going to solve for y.
Mm-hmm.
like to find the function, like what is y equal to? So you're going to solve for y equals. In this case, we didn't solve for y equals because we knew the answer and it was going to be in the form of x squared plus y squared equals c. So it's not about isolating the c so much as it is solving for what y is equal to after you any differentiate. Okay, so there's sort of two like tiers of what you're going to be doing. First, do the grouping, any differentiate, then do the next grouping. All right, let's take a look at that's not where I wanted it. That's okay. Let's see. Oh, I wonder. Okay, I got that. Okay, let's take a look at 19. So we have dy dx is equal to y squared. All right, first step. You can cross multiply, right?
dy over.
Cross multiplying here is going to be a little bit of a bummer, though, right? We could, though. It doesn't matter. You can still do it as a first step.
dy times y is negative 2. What's the x?
So I might actually multiply both sides by y to the negative 2. So we get y to the negative 2 dy on this side, and then on this side we get dx.
To get rid on the bottom, so you have the y side.
Right, if I want the y squared over to the other side, I have to divide by y squared. Dividing by y squared, is that all right? Okay. Well, all right, because I'm going to do this, and I just wanted to leave room to do that. I will do the right-hand side. Oh, no, I won't, because that might throw people as well. Okay, that's fine. I won't do either side. Someone do the y side. What's the antiderivative of y to the negative 2? Helen?
Negative 1. Or, no, just negative 1.
Negative 1/3 y to the negative 3.
I'm kind of dizzy. Can I do like that?
Mm-hmm. That'd be great.
I'm really dizzy.
You should
Really dizzy.
walk her to either get something to drink. We'll see. Gosh, I should have screencast the other class today. All right. I know. Oh man, what's the
That's so scary.
what's the antiderivative of dx? No, close.
0.
No.
1.
Actually, there is a 1 right here, if that helps. It's going to be x plus some c, and maybe I should put c1 and c2. I think I'm going to do negative 1 over y is equal to x plus c. Does that make sense?
Yeah.
Like I just put the c on the other side, and when you have c2 and you subtract c1, what do you get? You get c. Yeah, it is c3. I know it's my last c, so I'm just going to call it c. And and then maybe I will call it c3 because I'm going to multiply through by negative 1, and get negative x. Instead of saying minus c3, I'm going to say plus c4.
You have C4? No.
It's like I could say minus c3, but it's just a constant. So y equals 1 over negative x plus c. Just flip both sides.
This incident stole in my mood.
I'm just trying to finish this one up, and then we're not finished yet though. They give us a piece of information that y1 of 1 equals 1. We can actually use that to solve for what c is. So we know that y1 equals 1, or when we plug 1 in, we get 1 equals 1 over negative 1 plus c. So c must be 2?
Yep.
Y equals 1 over negative x plus 2. And that's the solution to that differential equation. You want to ask a question on it?
Looks pretty.
let me, I don't want to do it.
Not too bad.
No, I actually think most calc students sort of like it. It's like a little algebraic. It's straightforward. Like there's sort of a pattern to it. Let me just start 21 for you because it has a slightly different strategy to get started, and it's just algebra. But the first thing we would do is isolate the differential part, so we'd get 50 minus 2b. Now here the important thing is to understand that you can't just add 2b back to the other side and separate the variables. This whole thing is actually an entire quantity. So when you think about separating the variables, think multiplication and division, not adding and subtracting. So to set this up, it would be 1 over 50 minus 2b db equals dt. Does that make sense, that strategy? Steve? Dom? And now you could actually do this, and I'd be inclined to do the right-hand side and say, oh, that's going to be t plus c. And just to test you out, what would the antiderivative of the right-hand side be? Did I say right? I meant left.
Oh, yeah.
Left-hand side, what would that be?
-1/2.
You're really close.
Rewrite it.
Well, what do you want there to
Can
be?
you rewrite it for me?
Let's rewrite it right to the negative
It's 1/2.
Oh, no, you
No,
can't.
take the ln.
ln. Yeah.
It's screaming ln. Helen was alluding to, I don't know if I'm putting words in her mouth or not, that we need the chain, though, of -2, so there has to be a -1/2 out in front. And once you have the chain, you can say -1/2 ln of 50 minus 2b. I definitely want to come back to the algebra involved in doing this because you can see you're going to do some like pre-calc where you're going to take like e raised to that power. Yep, sorry, you're absolutely right. Helen's saying I need another plus c over here. I need to do a little bit more algebra with that. We'll do some more tomorrow where we're doing some of the algebra involved in solving an equation like that. But that's a good place to stop and pause. And let's see. I have homework that I can